Let me start by saying that today's presentation is on behalf of the whole ACT collaboration. Here you see a picture of us featuring more than 100 scientists at 41 different institutions spread over 7 countries. And I really wanted to say that all the amazing science we can do with ACT is thanks to the contribution of every single of these members. So for today webinars, the main topic is going to be cosmological constraints inferred from the power spectra of the new ACT data release 4 or DR4 maps. And these results are described in these two papers, Ayala et al. And Choi et al. Posted today on the archive. But there have been a number of different analyses that have sprang from these maps. Today also on the archive appeared this paper from Sigernes showing a combination of the ACT and Planck data set to produce 40% of the sky, high resolution, and very sensitive maps. Here you can see a little sneak peek from that paper showing the high resolution information added by Planck. But also the reconstruction of lensing maps over roughly 2,000 square degrees. Here you can see a map from that paper. Constraints on cosmological birefringence, as well as using the multi-frequency information of ACT and Planck to create component-separated maps for CMB and TSZ. And I should say those are the papers that are already posted, but a lot more is coming up and will be shared with the community in the next few months. But of course, today we are focusing on these first two papers. And as I said before, it is work of the entire collaboration, but I want to get the chance to highlight the people who have focused a lot on the analysis that led to these two papers, and you see the teams here. And the other point I want to make is that these two papers are very connected, and in order to get a comprehensive view of the topic of the analysis and the results, they should be read together. So, as you may know, ACT is part of a much broader community of ground-based CMB experiments that are currently operating. And this plot shows you CMB experiments at the South Pole with blue crosses, CMB experiment in Chile in the Atacama Desert with orange circles, and here there is ACT. From the x-axis of this plot, with resolution from the telescope increasing from left to right, you see that ACT is an arc-minute resolution experiment that over the years has increased the footprint, observational footprint over the sky, now reaching roughly 40% of the sky. Also featured in this plot, you see the two main CMB satellites, WMAP and Planck. They have concluded their missions, but they're included here because throughout this analysis, we'll be using these two different data sets, satellite data sets, either in comparison or in combination with ACT. So we will be focusing on these three showing the pictures. So what's this new measurement? We have a brand new measurement of the cosmic microwave background, CMB, in both temperature and in polarization. Here I'm showing two cutouts of 150 gigahertz maps that are Wiener filtered to highlight the features. And these cutouts are roughly 15 degrees in rate ascension and 10 degrees in declination. And on the left-hand side, you see the temperature map, which is really showing the density fluctuations of the plasma at a redshift of 1100. On the right-hand side, instead, you see a beautiful map of the polarization of such fluctuations, what we call the E-mode map. And what this is showing you, coming from the same physics, is the velocity field at the last scattering surface from that plasma. So this is a new measurement, very high resolution and very deep. And how do we compare with Planck, for example? Well, we can check this visually to start with. So from next slide, you see that when we add ACT and Planck, I'll try to flip back and forth. As far as the temperature is concerned, adding Planck, what we really have is that the large scales that a satellite experiments can access, very well measured, that you see here. At intermediate scales, Planck and ACT provide two independent measurements of such modes in the sky, and then ACT adds a lot of small-scale feature at IRL. As far as polarization is concerned, you can see that there isn't a big difference. And although Planck has a beautiful measurement of the mode power spectrum at the map level, the noise level is not low enough to be able to see these features on these scales. So very complementary. And so the idea is that having in hand this new and rather powerful data set, we realized that we can put constraints on cosmology and really giving an independent measure of cosmological parameters and compare those to Planck to weigh in on the robustness of Planck's findings as well and compare to those. And we are at the level where this data set is good enough, is strong enough to really put constraints with comparable error bars. One of such constraints, of course, within Lambda CDM is the estimate of the Hubble constant H0. And from this analysis, the value that we find is 67.6 plus or minus 1. These numbers comes from combining the ACT temperature and polarization data with the large-scale information that satellites like WMAP can access. So when you combine these two, you find this data point with this error bar, and this is our baseline result. I just wanted to point out that even if we don't include WMAP, that result is very consistent, just with slightly broader error bars. In general, our baseline result is in complete agreement with what is found by Planck public release 3 that is shown here. We agree with Planck within 1 sigma. And of course, because of this agreement, we confirm the previous findings on H0 when comparing our values or Planck values to values of H0 inferred from supernova 1A calibrated with different methods. And specifically, we agree within 1 sigma with measurement using the tip of the red giant branch as a calibrator, and we confirm roughly 4 sigma tension when comparing with Cepheids as calibrators. And you can find more of this in the papers as well. One last remark that I want to make is that all these very beautiful maps, as well as intermediate products, sorry about that. Beautiful maps, as well as intermediate products and likelihoods, are available on the NASA Lambda website, and they are there for the public to use and explore. And we understand that this data set can be slightly different compared to what the community is used to with Planck. So so we also made available IPython notebooks for the community. And with that, I leave it to Marius Lungu, who will be describing the instrument and the characterization of the instrument.
Great, thank you, Simone. I will be discussing some of our data sets, specifically where our current data set sits in the context of what we have already observed with ACT and some of the future data that we have already collected and are already beginning to analyze. So as you can see over the timeline shown in this slide, we originally started observing with ACT back in 2008 with a non-polarization receiver with 3 arrays at 150, 220, and 280 gigahertz. This data was formed part of our first 2 data releases DR1 and DR2. We then changed our receiver to be polarization sensitive. Starting in 2013, we started observing data with the ACT pole receiver with 1 array at 150 gigahertz, later adding another array at 150, and then a third dichroic array at 98 and 150 gigahertz. These 3 arrays form the set that we are discussing today of our 4th data release. We had a DR3 3rd data release based on data of just PA1 and PA2 back in 2017. So we're extending this now to more arrays and much more sky coverage in our current data set. We also have a wealth of data that we have observed since the ACT pole experiment has transitioned to advanced ACT with 3 new arrays covering 150, 90, and 220 gigahertz. And we're also started just observing with a low frequency array at 30 and 40 gigahertz. All of this data is already in the can, so to speak, and a lot of the infrastructure that we've developed for our current data set is already being applied to this new data set for analysis. So let's briefly review where our data was taken on the sky. Here I show the various fields that we've observed as part of our DR4 data set over the years. These are in galactic coordinates. So in our first season with one array, we've observed 3 deep fields, deep 5, deep 6, and deep 1. These were smaller compared to some of the other ones that we observed in later seasons. Our next season, we observed a slightly bigger field, deep 56. And in our third season with the new dichroic array, we expanded our coverage even further, including deep 56, Boss North, which overlaps with an optical survey, and deep 8 in the southern part of the sky. In season 16, the last season that's part of this data release, we really expanded our coverage to the advanced ACT region, which is now we've continued to observe for a while, including today's observations. And this field is shown right here, observing over 40% of the sky with all these arrays. Next, I will show you some maps depth for our maps that we have released over this data release. Here at the bottom, you can see our 150 gigahertz map depth across the sky with the Planck 353 gigahertz map in the background, showing the galaxy. As you can see, there are various deeper areas in the maps, deep 5, deep 6, deep 1, and deep 56, and deep 8, and then Boss North over here. These fields, like I said, were observed somewhat deeper, and then you can see the sort of shallower regions here, which really cover a large portion of the map. Those are part of the advanced ACT survey that we began in the later seasons and continue today. One thing to note is that even though these regions are shallower at some degree, we still have over about 4,000 square degrees with noise that's equal to or better than Planck's 143 gigahertz full sky map. Here we see the 98 gigahertz equivalent. At this rate, we have almost 9,000 square degrees with noise that's comparable or better than Planck's 100 gigahertz full sky map. And these are white noise level. And so you can see that some of the coverage is slightly less deep, and this is because we only started observing with our dichroic array, which contained the 90 gigahertz channel only in later seasons. The plot on the top right shows the cumulative area below a certain noise level in our maps. And then here you can see the various different frequencies across our data release and the combined sensitivity for the map, and the Planck scale noise levels highlighted here. Also to note that we do have regions that are quite deep, almost 600 square degrees at better than 10 microkelvin arc minutes. And when you add additional data from advanced ACT, as is shown in Ness et al., this increases to about 2,500 square degrees. So it's quite an impressive data set that we are continuing to analyze and will move forward at full steam. Next, I wanted to show some maps that we took with this current data release. Does not cover the entire coverage that you saw earlier, but I wanted to highlight specifically here the deep 56 regions, which is quite deep, showing the temperature fluctuations here. The map depth of this field is roughly 11.5 microkelvin arc minutes, and you can see the Scholar scale here is plus or minus 250 microkelvin. We have these kind of high resolution measurements of over approximately 40% of the sky, and I only show a cutout here of one of the deeper regions. We also have polarization measurements that are quite good. Here at a map depth of 16.3 microkelvin arc minutes for the same field, you can see here the typical cross and X-shaped features that are typical of E-mode polarization in our map. So these are signal dominated maps here. The color scale is roughly plus or minus 30 microkelvin. And here, Simone already showed a map earlier, but here's a much broader map showing that we here are signal dominated in E. Over this particular portion, you can clearly see the fluctuations, and we are signal dominated in E over approximately 4,000 square degrees on the sky, so a big survey area. We also show here the B map, which is basically equivalent to noise in the same context. So if you flip back and forth, you can see really how the signal of the E maps kind of stands out. In the bottom right here, you see a small polarized point source, which looks like a quadrupole when transformed to B modes. Finally, before we transition to the power spectra, I wanted to briefly review that there was a lot of care taken in the way that we analyzed our data and looked into various systematic effects that we wanted to check for and make sure that we're happy with the data. There will be more discussion on the spectrum level checks in the upcoming slides. I just want to briefly highlight a few here. We improved beam modeling for our experiment. We've included the scattering effects of the optics and the primary mirror. These are treated in the L-space window functions, which get applied to the power spectrum. We also wanted to check that we weren't in any way biased in our calibration range at high or low L ranges. Here, from 600 to 1200 and 1200 to 1800, we did a check of comparing calibrations in these two ranges when we did our single calibration to Planck, and they come out to be quite close and within our overall calibration error. Finally, we looked at our temperature to polarization leakage and found that it is quite small. You see at the top right a plot illustrating the L-space polarization leakage that we found from measurements of Uranus, which you see some measurements down here in the bottom right in the form of polarized beam maps. We also did a continuation of our analysis of polarized near side lobes, which you see in the top right plot here for PA3 from our previous release in Louis et al., and wrap that all into our temperature polarization leakage analysis. Like I said, though these numbers are quite small, we still account for them in the parameter likelihood, which we'll hear about later. So with that, I'd like to hand it off to Steve Choi from Cornell University, who will be talking more about the power spectrum.
Thank you, Marius. Yes, I'll discuss the power spectrum analysis done on these maps presented by Simone and Marius. So just to recap, here is a map showing the galactic dust intensity in the background from Planck 353 gigahertz. And on top of it is the coverage from ACT for DR4. And so this table shows, lists the different fields that we have observed for DR4 over these 4 seasons from 2013 to 2016 with these 3 different detector arrays, PA1 and 2 at 150 gigahertz, and the third PA3 dichroic array at 98 and 150 gigahertz. And from 2016 and on, we started doing this large sky area survey that we call Advanced ACT, AA, and it's about 17,000 square degrees. For our power spectrum analysis, we select about 5,400 square degree in effective area, which accounts for the hit count variation. But I should note that from 2017 and on, we have a lot more data taken on this large sky area with the upgraded Advanced ACT pole instrument. So it's filling out the shallow area to be much deeper, and we expect our, the effective area that we'll analyze for the power spectrum to be substantially greater than what we're presenting here today. And so with these different regions, we first characterize the noise. So we, as an example, looking at the Deep 5-6 region, here are the noise power spectra shown for the Deep 5-6 region in TT in colored solid lines, which are the different detector arrays, PA1, 2, and 3, and they're shown relative to the expected CMB TT spectrum in gray. And you can see in temperature, we do have this large 1 over L or 1 over F noise relative to this white noise fit shown in faint dashed lines. And this is due to atmosphere. But nevertheless, you can see that a lot of these modes are signal dominated, meaning these noise power spectra sit below the expected signal level. And also in polarization, where it's not affected by atmosphere as much, our noise properties are a lot more white. And so for Deep 5-6, we measure a lot of these modes to signal dominated regime. And to add information, we need to go and observe more sky area, which is precisely what we do. And so for all these different regions, we characterize the noise and have noise simulations and signal simulations. So with these simulations, we compute the covariance between different power spectra from different arrays, and also check the consistency of our data. And so here's a slide summarizing a large suite of internal data consistency tests we have done. And as mentioned, for each region, there's observation coming from different arrays over different years. So you can take, say, the Deep 5-6 region. This map coming from two different arrays or two different times. And we expect the signal to be the same in these two maps. So when you subtract the two, you should get something that's consistent with noise. And so this is what we do in two different ways, taking the power spectrum of the difference of the maps A and B, or taking the difference of the power spectrum of the maps themselves, maps A and B. And there ends up being 438 total pairs where we can do this null checksum. And for each of these, we have 500 simulations run. And for these null power spectra, we show these chi-square distribution for data in yellow and simulations in blue. And they're both normalized to have unity area. And you can see that there's good overlap, good consistency in our data, meaning our data is described by our simulations. And on top of these, we have a lot more internal data consistency null tests that we have run that's summarized in the paper. So after going through this large suite of internal data consistency tests and passing them, we look at cosmology from our spectra. So with these, we co-add the different, the power spectra coming from different years and seasons, different seasons and arrays into a single frequency spectrum at 98 and 150 gigahertz for TT, TE, and EE shown here for the deep region. What we call the deep region, referring to deep 156 and deep 56. And when I flip to this next page, the power spectra, co-added power spectra coming from the wide region, BOSS North and Advanced ACT from season 16. And we also have 98 cross 150 gigahertz that we just do not plot here to keep these plots uncluttered. And when I flip back and forth between these two sets of power spectra, one difference you see is in this high L small angular scale TT power spectrum, which is a difference that's expected, and it's coming from the difference in the source flux threshold that we apply to mask the sources. So basically, these are just extragalactic foregrounds that are different in the two different regions. And we should be focusing on these peaks and troughs where we're dominated by the CMB, primary CMB spectra. And we do these checks between internal consistency check between the deep power spectra and the wide power spectra, also between 98 and 150 gigahertz, which we'll hear more from Arminia later. And we're measuring a lot of these modes to a signal dominated regime in some of these fields. And again, we added area on top of it, which is helping with the cosmological constraint. Again, we'll hear more from Arminia on this. And when we combine the deep and the wide patch power spectra, we get these combined error bars shown in blue for ACT compared to the other experiments shown in log plot. So purple is Planck, who is doing well at this low L or small or the large angular scale, excuse me, and coming from their full sky survey, and SPT, who is doing well at this high L or small angular scale coming from their deep but smaller fields. But in the intermediate scale, where there's a lot of peaks and troughs, ACT is starting to do well, especially in polarization. And again, this is helping us constrain the cosmological parameters, as we'll hear from Arminia. And with these, we have the co-added CMB power spectra for TT, EE, BB, and TE from ACT DR4 after cleaning out the foregrounds. And here is the best fit Lambda CDM model from ACT plus WMAP in solid line, and dashed line is just a Planck model. Lambda CDM is a good fit to ACT data. And finally, here's a plot showing comparison with the other experiments in the field. And this is just remarkable to see what we are achieving as a field together. So really congrats to everybody for this. And with this, I'll hand it off to Arminia Calabrese, who will describe the cosmological parameters from our power spectrum.
Okay, right, I'll take it from there and head to cosmology now. Okay, so the spectra that Steve has presented are then modeled to include the CMB as well as other additional galactic and extragalactic source of emission, as well as corrections for polarization efficiency and beam leakage in what is an actual full likelihood product. And this likelihood is then used for two main applications. The first one is to derive our act-alone baseline results and compare these with a number of robustness tests that we can run on our data. So here you see an example of that done for the H0 parameter, where we get the estimate in our baseline scenario, and then we compare it with what we get when we only use a subset of our data. So for example, when we use a different minimum multiple in our analysis, or if we only use one of the CMB probes, or only one frequency, or only one sky region observed by ACT. And what you see is that our results is really robust against these data cuts, and we really see that the solution is quite stable. The other application that you can use this full likelihood for is to isolate and extract the CMB-only power that is present in your data. This is done again in Choi et al. And shown here on the right with this CMB-only spectra, now showing the TT, TE, and EE CMB power. And these spectra now already include uncertainty due to foreground emission and other corrections that have been made to the data. These are packaged in a different likelihood product, the actual light likelihood, which is now ready to go for cosmological analysis. So in Ayala et al., we take this spectra and we explore a number of cosmological models. We find that our data are well fit by the basic Lambda CDM model. And here on the right, you see a plot of the 6 basic Lambda CDM parameters and 2 derived parameters of interest, including H0, that we derive from our ACT DR4 CMB spectra. And you also see the equivalent that you get when you run Lambda CDM constraints by using WMAP alone or Planck alone datasets. You see that we have good consistency, and if we wanna give a more quantitative assessment of these, we can look at the full multidimensional parameter space to come up with an answer telling us that the ACT solution is at the 2.3 and 2.7 sigma level, consistent with results from WMAP and Planck. The main difference is in this baryon density and scalar spectral index parameter space, which is affected by the fact that ACT is not measuring the very large angular scales. Another consistency test that we can do in Lambda CDM is to look at the measurement of the lensing smoothing in the ACT power spectra, which in Lambda CDM is expected to give an amplitude for this lensing parameter of 1. And as you can see from this plot, we recover the expectation from Lambda CDM with ACT really well. Okay, so now that we have assessed the cosmology from ACT alone, we can go ahead and add some large-scale data to ACT to tighten even further our cosmological results. But we also want to give a cosmology that is independently measured of Planck, and for this reason, we chose to combine ACT with WMAP. So here you now see the same plot as before, but comparing ACT plus WMAP with the Planck alone result, and then the combination of ACT plus Planck. And you can just see that all parameters agree really well between these now 2 independently measured CMB datasets, ACT plus WMAP and Planck. And this is true for all parameters, but I want to highlight again the agreement, the excellent agreement that we find on the Hubble constant. I also want to remind people that this parameter is a derived parameter in Lambda CDM, and it really comes from pinning down 2 basic parameters of Lambda CDM, One of them is the peak angle, which is measured by the position of the acoustic peaks in the CMB power spectra. And the other one is the cold dark matter density, which is instead measured by the relative heights of peaks in the CMB power spectra. We also explored a number of models beyond Lambda CDM. We have considered a number of single parameter extensions to Lambda CDM and two groups in particular. So some parameters that are more sensitive to the primary CMB anisotropies, for example, the effective number of neutrino species or helium abundance and the running of the spectral index, or parameters that are affected by the amount of lensing present in the data, for example, neutrino mass and curvature. All the results are summarized in this dense and colorful plot where different colors highlight different models that have been explored and different symbols distinguish between different data combinations. The takeaway message from all these results is that we don't see any strong deviation from Lambda CDM, and all these extended parameters are within Lambda CDM expectations at 1.5 to 2.2 sigma level. And in particular here, we zoom on the curvature parameter, and we see that with the ACT data, we have no evidence for deviation from flatness. Okay, and to conclude, I just want to go back to what was already said earlier by Marius. This is only a fraction of the data that ACT has collected, and ACT is due to observe until 2021. We already have over 4 times more data than what's been analyzed in this DR4 already in hand and under analysis. For cosmology in particular, we are hitting the regime where polarization is more constraining than temperature. And we are also widening our frequency coverage with a low frequency array observing during 2020. There will be lots more science to come in the next months. In particular, there will be lensing, cluster, and KSZ analysis on this dataset. And I also want to remind again that all data and products are public and available on the NASA Lambda website, together with tutorials and IPython notebooks to learn how to use our data encodes. And there will be more seminars over the summer on other scientific results. And this is the end of the presentation, and now I will hand it over to Mark, who will be coordinating the questions.
Okay, thanks, Armenia, and thanks to everybody, all of our speakers. And we've got quite a few questions. I want to say 2 things. I'll remind you again from what Suzanne said is that the video of this webinar will be posted on the, at least a link to it will be posted on the ACT website. So if you want to review what's been said, please refer to that. If I don't get to your questions, then I'm sure that you can send an individual question to one of our presenters after the webinar. Okay, with that, let's get started. The first question we're going to look at is to Armenia from Mark Kamiankowski. Can you describe how much cosmic covariance there is between your results and the Planck results due to the fact that you're looking at the same sky or overlapping? To make it a bit more quantitative, you both have similar error bars to H0, but what is the covariance between your H0 and theirs?
That's correct. So yes, we look at the same sky. What we have presented here is an independently measured H0 value rather than a completely independent new estimate. So yeah, that's correct. Those 2 measurements are correlated. But we also have a stronger correlation in the low to intermediate temperature spectra and less correlation at high multiples and in polarization. So I don't have an overall number to quantify that, but they are not 100% correlated.
Okay. And again, from Mark, do your new results have anything to say about the Planck AL anomaly?
Yes, so that's something that I've shown in my slides. So James, if you can go back to my previous slides. Next one and next one, sorry. Next one, this one. Yes, so slide 40, please. So yes, we provide a new estimate of a lens. We don't see any departures from the expectation from Lambda CDM, but we're also consistent with the distribution from Planck. So our interpretation of this is that we don't see any deviation, and this could, the Planck estimate could well be a statistical fluctuation in this scenario.
Great. Okay, Marius. The Planck noise depth, oh, this is from Rejo Keskitalo. Sorry if I didn't pronounce that correctly. The Planck noise depth is not uniform. When comparing the noise levels, would it work to arrange the Planck maps by noise depth and compare the equal sky fractions with the least noise? Another apples to apples comparison would be to use the same sky area for both.
Yes, that is a good point. We can certainly make a plot like this. And what I can say also is that a lot of the area that we cover in this data release is in some of the more sensitive regions for Planck. So yes, we can definitely do that.
Okay. Thanks. Okay, this question is for Simone, and James, could you flip to slide 9? Can you help motivate why the ACT DR4 plus WMAP value for H0 does not lie between the individual constraints from the ACT DR4 and the WMAP? Basically, the error bars are, the mean values don't add up.
Yeah, sure. I should point out that when we look at a single parameter, this is sort of a very skewed view of that. As Ermina pointed out, this is very much a six-dimensional parameter space. So what really matters is how the different data sets in this high-dimensional parameter combine together and cut several degeneracies. And so when we marginalize over all the other parameters to extract H0, this is actually this result is just fine. There is not necessarily expectation to lie in between the two measurement because of these correlations between parameters and this higher dimensional space.
Great. Thank you. The next question is from Wendy Freeman, and I'm going to have Steve take a look at this one. Can you say when you will have polarization measurement constraints on theories of, for example, early dark energy and other potential physics beyond Lambda CDM?
Right, I believe we have colleagues that are working on this right now, right? And some of the results should come out soon. I'm not sure if I could say exactly when.
We're working on it.
Yeah.
Okay. All right. Next question is for Armenia from Georgia Stafiu. What have you done for tau? Very simple question.
That's right. So ACT doesn't measure tau on its own, so we impose a prior on that parameter. It's a Gaussian prior centered on 0.065 with an error of 0.015. And it's a very conservative prior because, as I said earlier, we wanted to give results that were as independent as possible from the measurements from Planck. But we have tested different mean values and different errors on tau and how they impact the results, and there is very little impact, for example, on H0. It really only affects the amplitude parameter.
Okay, thank you. Again, from George to Armenia. When you compare with the Planck, for parameters such as a lens, which Planck likelihood do you use?
So we use the final Plick likelihood of the Planck 2018 legacy release, but we use the same tau prior that we used for ACT to give consistency across runs. So that's Plick in temperature and polarization plus a tau prior and the low-L data from Commander.
Great. Okay, again for Armenia from Ira Wolfson. In H0 separate component analysis, why is the EE alone above so high?
I guess this is referring to the consistency tests we've done. One thing I didn't mention when I went over that plot is that there is also the expected shift in parameters that you have by the fact that you are only considering a subset of the data. So the jumps in parameters that we see seems really consistent with what you expect. And EE is our less constraining channel at the moment, so it goes higher with a much larger error bar and within expectation from cutting data.
Great. I'm going to send the next question to Simone. Can you briefly comment that using the why, when using the active data alone, you find NS greater than 1?
You're muted, Simone.
Sorry, thank you. Yeah, sure. So as Erminia said, we don't measure the large-scale information, and that's information that we get from WMAP. And again, we are in this 6-dimensional parameter space, and when you look at data only from high L, the degeneracies between NS and omega B, as she showed, are different. This is basically coming from the fact that we cannot measure this low L information by ourselves, but then when you combine back with WMAP, we get a consistent result. And I should say, I don't know, Edwin, if you want to add anything.
Yeah, well, just to say that ACT in a the ACT results lie on a degeneracy line, which is affected by both having lacking data on large scales and also our TE solution compared to what WMAP and Planck want is slightly lower, and that's why ACT lies in that specific region for NS.
Great, thanks guys. Okay, next question is for Steve. Can you describe the blinding analysis that was used for ACT?
Yeah, for this, maybe we should go to the backup slides, James.
By the way, when I'm not mentioning names, this means we've gotten multiple questions about the same topic.
Yeah, the next one, please. Yeah, so, right, so we sat down together before we started this whole analysis and decided on these many things that we'll test before we look at the cosmological parameters. We have looked at the power spectra, but we have never plotted any theory curves on top of it. And I mean, none of us could measure cosmological parameters just by looking at the band powers themselves. So we were looking at the power spectrum, and we had compared to the previous data power spectra, but until we have passed all these parameter or all these power spectrum data consistency tests that I've described and other null tests, we have not looked at the parameters. And further, we have not looked at the parameters until we have also looked at the null between the parameters coming from, say, the 2 different frequencies or 2 different areas. And then, yeah, so after all these checks, we unblinded. So we're, yeah, that was the blind analysis.
Okay, so the next, thank you. The next question, I'm going to have Simone answer. There are other cosmological distance ladder measurements, Mazur's, Tully-Fisher's, and so on. What is the tension between ACT and the mean of the various recent distance ladder measurements?
Yeah,
that's from Adam Rees, by the way.
Yeah, I don't have a number to provide. I would say though that since our result is consistent with Planck, broadly any tension that was noticed before with Planck will hold true even with our data, perhaps at a slightly smaller significance just because of error bar correction. But we very much agree with Planck, so everything will still hold. But I don't have a number for you, sorry.
Okay, and a slightly more philosophical question from Adam. If the age of the universe is proportional to the inverse of the Hubble constant, and there is a tension between the CMB and the local measurements of the Hubble constant, how well can we really say we know the age of the universe? Just a moment.
Yeah, so I guess to answer that question, I can point out to one of the appendix in Ayala et al., where we try to basically explore how the age of the universe changes while imposing an H naught of sort of 74, but also making sure that we can feed the data, the CMB data. And the age does vary a little bit between, I remember, something like 13.6 to 13.8. So I guess depending on which data set you would like to include and what kind of priors you want to put on those, you get this range of ages.
Okay, thank you. Next question is from Rohan Naidu, and I'm going to send that to Armenia. Could you tease any constraints on reionization you're finding, e.g. on the duration of reionization from KSC plus tau?
Not from this analysis, because we didn't do, we only used the minimal foreground model that we need to model our data, but we didn't go into the details of the KSZ modeling, for example, which is strongly correlated to the CIB modeling, and therefore a more thorough analysis of that is needed to provide those constraints.
Okay, thank you. Next question I'm going to send to Steve is from Gary Hinshaw. Do you expect to be sensitive to EB leakage from lensing at high L soon?
Right, so our survey for ACT and our analysis pipeline doesn't optimize on BB yet, but nevertheless, for this very wide area that's shallow, we do have a BB measurement that's substantially improved from last. And we expect that when we include all the data that we have taken from 2017 to 2020, we expect this will improve much better, improve to a much better value.
Okay, thank you. I'm going to send this one to Simone. And this is from Mark Kaminkowski again. How significant are aberration effects, i.e. those due to peculiar velocity with respect to the cosmic rest frame?
Yeah, since we do have a partial sky measurement, of course, we are biased by the, we have an effect from aberration. I should say that this was already taken into account in the previous data release from ACT, where we were observing only a small patch of the sky that is actually centered around on the negative direction of the boosting. Now we are on a much larger sky area that actually covers both positive and negative parts of that boosting map. And so the overall effect is smaller. However, we do correct for that in our power spectra, and the constraints are cleaned from the aberration effect.
Great. Okay. So for Steve, this again back to the blinding. Can you comment on your post-blinding data cuts, and what are the elements that allow you to be confident that the rest of the data is okay?
Yeah, the elements are the suite of large tests we have done, but we still find that for low LTT, which ACT does not measure well, we have a deficit in power compared to Planck or WMAP. So this is how we implemented this cut in TT after we unblinded. We have also looked at TE more closely for leakage, and this does not have any impact on our baseline results.
Okay. This is Douglas Scott to Armenia. Mostly seems that the new ACT results reduce some of the previously claimed tensions and anomalies. If we're to look at these results and with the hope of finding something new, where would you say the strongest hints might lie?
I think the power of ACT here is the new increased sensitivity in polarization. So if we have models that can be more characterized with polarization, they can get better constraints from ACT now.
Okay. Next question I'm going to send to Simone. Do you expect to be able to get a good estimate of the bispectrum or higher order from these data?
Yes, I don't have a sigma number for that, but I will point out to a previous analysis from the ACT DR3 on the ACT DR3 maps, where second order statistics were like bispectrum were computed on and used to constrain to put constraints on the different shapes. And definitely this data set is going to be powerful, both because we are reaching a noise level in a very large area of the sky that is low both in temperature and definitely in polarization. So we will improve on constraints from that quite a lot. I don't know compared to Planck, but definitely we'll add more weight on the polarization side of things. But yes, has been done before and will be done.
Okay, to Steve, is your E-mode polarization data from primary CMB anisotropes alone, or do you combine E-mode data from secondary anisotropes?
Could you repeat the question?
Sure. Is your E-mode polarization data from primary CMB anisotropes alone, or do you combine E-mode data from secondary anisotropes?
These are the primary CMB. If the question is asking about something like lensing, then it's not included here.
Okay. So next question is for Armenia. You said earlier that your ongoing observations are becoming so deep now that the polarization signal becomes the dominating constraint to cosmological parameters. Can you elaborate a bit more on this, which those parameters are and how the covariances change?
Yes, so we are hitting a regime where constraints for polarization become comparable and eventually more constraining than temperature. We already have examples for some parameters in our current release, and we have a nice appendix in the Aiola paper where we show, for example, that our dominant constraining power from H0 is already coming from TE, for example. So yeah, in the future, this is only due to increase.
Next question is again for Steve. Have we done direct band power comparisons with Planck on the same regions and frequency bands smooth to those to fixed noise level?
Yes, so we have done a direct comparison of Planck in our regions. At the power spectrum level, we take ACT cross-ACT power spectra and ACT cross-Planck and look at consistency on those. And we find good consistency in polarization, but we do see a mild tension in temperature across TE power spectrum. And both Planck and ACT have temperature to polarization leakage. And we have studied our leakage model exhaustively, but we do not have yet Planck's leakage model in these regions. So we couldn't do a complete apples to apple analysis yet. And we hope to do this in the near future.
Okay, again, a slightly more philosophical question, which I'm going to send to Simone. Why so much emphasis on H0? H0 is derived parameter within Lambda CDM. Does not make much justice to the data. I think I would think that NS, WB, RS are closer to what the data really tell.
Sure, I would say that in the paper, we definitely present a comprehensive view of Lambda CDM. And I agree that H0 is a derived parameter, and we can, transfer that to a beautiful measurement, as Armenia said, of the theta parameter and the omega B parameters as well. We do have some effects that we see in the NS omega B plane, which I think at the current with the current constraining power, we cannot draw any strong conclusion. In the near future with more ACT data, if those are real problems, they will show up a higher significance. And so I think we'll continue to address this more. But I think in this specific couple of years, H0 was one of the very much discussed parameters, and we hope that right now, having ACT and Planck agree at a degree that it's so good, also comparing the error bars, strengthen the fact that Lambda CDM and specifically H0 are well measured from the CMB.
Great. Okay, for Steve, is there anything new regarding constraints on the early universe? In particular, any improvement in the tensor to scalar ratio R from B modes or primordial non-Gaussianities?
Yeah, as I said earlier, we have not optimized our analysis to be good for low L polarization, and our survey strategy and analysis focuses on these large area for measuring a lot of these CMB, TT, TE, and EE modes for these cosmological constraints.
Okay, I'm going to handle one fun question myself. on the title slide, what are you cooking in the ground screen that creates the purple and blue steam? I think that one answers itself, but that is a nice picture that my student, John Ward, took a couple of years ago of the galactic plane. I am running out of questions here, so if people have more, you should mount them up, put them up now. Oh, here we go. This is a comment from somebody, but I'm going to send it to Simone. It should be mentioned that there is already a Planck-independent and strong constraint on H0 galaxy surveys. But I think we've already talked about that.
Yeah, no, absolutely. It's beautiful that we can probe cosmology and put constraints on parameters with many probes, galaxies, CMB, and supernovae, and it's definitely true.
Great. Okay. Well, if there are no more questions, wait, one more. We have a little more. Oh, here they come in. Okay. Okay. Oh, this will go to Armenia. Can you talk about the availability of foreground polarization maps?
We haven't, there have been some analyses that have looked at component separation, putting together ACT and Planck data that are presented in other papers. So not linked to this specific, these specific products from these papers presented here.
Okay. And Armenia also, this is now specifically to the parameters. Omega K seems to differ a bit. Is this just noise?
Seems to differ a bit. I guess that's between ACT and Planck. I don't know if the question is exactly that one. If so, they are completely consistent within the error bars and within the two distributions.